Uh, okay, let me. So today I want to talk about a new paper that we posted around September on arXiv. It's a joint work with Marcus Curry and Professor Yao about a quasi-local mass in general relativity. So here is the outline of my talk. First, I will talk about quasi-local mass in GR. Then I will give a kind of Hamilton-Jacobi derivation of quasi-local energy. Then I will present, our new definition for quasi-local energy and mass with respect to Minkowski space. And I will give some results related to, properties of this new quasi-local mass, positivity, rigidity, and asymptotics. And I give a sketch of proof for, non-negativity. And at the end, I will give our current work and future works that we plan to do. So let's just start with the first part, which is the quasi-local mass in general relativity. So what we know from Newtonian gravity, that we have a Poisson equation. So Poisson equations, it's Laplacian of P equal 4 pi rho. Here, phi represents the scalar potential for gravitation, and rho is a mass density. So if you want to compute the mass, from calculus 2 in high school, you just integrate it over a finite region, and then you will have your mass using the mass density. In GR, the gravitational field is metric. So at each point of the space-time, you can go to a normal coordinate, and the metric looks like a Minkowski metric. So there is no density for gravitation. So the classical formula does not work. Now, the next best thing you can do, you can talk about a finite region of a space-time, and which enclosed by a surface, let's say call that sigma, and ask to define a new notion of energy inside this finite region of a space-time. So here you want to have the new definition based on the intrinsic and extrinsic geometry of the surface, sigma, which enclose, in this case, initial data set, omega-3 G and K. Okay. And this is sitting in your space-time, which is N3 and 1. Now, there is a famous, paper by Penrose, actually listed major open problems in mathematical relativity. The first one is to define a suitable quasi-local definition of energy momentum in general relativity. The statement of the problem is mathematically loose, which end to a plethora of different mathematical formulations for, quasi-local energy. One of that is by Bartnik, which look at a finite region of a space-time, a surface like sigma, and extend that to, asymptotically flat. Then you will have ADM mass. And when you take the infimum over all possible extension, you will have the quasi-local mass of that, surface, which enclose a finite region of space-time. There are other definitions using a Spinora and Twister by many people. Here is a list of them, including Penrose himself, using Spinora to come up with a definition for quasi-local mass. There's also work of Hawking and its generalization by Gerouch, which look at like a perturbation of FLRW or a spherical symmetric case, and came up with their definitions of quasi-local mass. There's also a different approach using Hamilton-Jacobi analysis. So the Arnovitz, Deser, and Misner definition, ADM, for energy and momentum use the Hamilton-Jacobi analysis for GR. They use the Hamilton-Jacobi analysis, these people like Butenman, Brown and York, Hawking and Horowitz, and later Liu and Yao and Wang and Yao, to come up with the energy, quasi-local energy in comparison to the original work of Arnovitz, Deser, and Misner. Note that all of these definitions, Butenman, Brown and York, Hawking and Horowitz, they assume, and Liu and Yao assume, that you have a reference Hamiltonian in Euclidean space, but Wang and Yao was the first one that assumed the reference Hamiltonian is actually Minkowski spacetime. Okay. Now, so As you can see, we have different definition for quasi-local masses and energies, but you can ask what are the expected, properties of quasi-local mass. The first one you expect to be is positivity. So you expect that it should be non-negative for a large class of surfaces in your space-time. It should have some sort of rigidity, so it should vanish for surfaces in the Minkowski space-time. It should have proper asymptotic behavior. When you go to the coordinated sphere and asymptotically flat, you should get ADM energy and momentum. When you go to asymptotically flat space-time, but this time in null infinity, the coordinated sphere, you should get the Binding-Sachs, energy and momentum. When you zoom in the coordinated sphere, very small, you expect that the decay goes like a Bell-Robinson tensor for a small sphere. If the surface encloses a horizon, you expect that you have some sort of Penrose inequality, like for the general Penrose inequality for total mass. And also some notion of stability for rigidity. So let's say you have a sequence of finite, initial data set with a boundary like sigma I. So you assume the mass of the quasi-local mass or energy of this goes to 0. You expect that this sequence converges to a finite region in the Minkowski space-time. So in this sense, has some notion of stability. You can add more property like monoclinicidity, subadditivity, to these, but here let's just talk about these one. What I want to highlight is there is no universal definition for quasi-local mass, NGR. And in this talk, we explore a new one, and we give a new definition, and we believe that this new definition can be the unique one, the one that has most of these properties. So let's talk about Hamilton-Jacobi derivation of quasi-local energy. Now, we want to consider a finite region in the space-time energy that satisfies, dominant energy condition, and that means the stress energy tensor in the direction of V and W is non-negative. Here, V and W are causal vector field, future-directed causal vector field. Now, if you pick the finite region of a space-time, you can pick a parameter like T and start to fluate this, finite region. Each one will enclose an initial data set like omega T, G, and K. And then you can write down the action and Hamiltonian. And then using, the constraint equations, you can drive, your Hamiltonian. So here, each one of these, triple omega G and K, we call that initial data set because there are solutions of Einstein constraint equation. In particular, there are solutions of trace of Gauss and Kodazzi equation. In here, the scalar curvature of G is R of G is the scalar curvature of G, and trace of GK is a trace of extrinsic curvature K with respect to G. And mu and J are energy and momentum density. Note that if you impose the dominant energy condition on the space-time, this will impose a condition mu bigger than norm of J in the initial data set. Okay, now we want to define the Hamiltonian. We pick an observer like T. And when you restrict T to the surface sigma, you can decompose it in the normal direction, which is future-directed normal direction M, and decompose it in the surface direction, which we call that shift vector Y. Okay. Now, both Amman, Brogniart, and Hawking and Horowitz, they came up with the Hamiltonian in this setting. You can write down the Hamiltonian of the surface sigma, which is a closed space-like surface of the boundary of this region, and you can express it in terms of the mean curvature. You can express it in terms of the extrinsic curvature in the normal direction and the shift direction. You can have also the trace of K, okay? You can re-express this expression in form of like the P and T, the metric product. Here, the P is a vector which is perpendicular to the mean curvature vector, okay? So this way of representing, actually, it's from the from the paper of Muta Wang and Yao. They represent it in this way. Note that in the derivation of the Hamiltonian, Braun-York and Hawking and Horowitz assume that each of these initial data set hit the boundary, the time-like boundary, orthogonal, but the first one that actually considered non-orthogonal case was Booth and Mon. So as a result, they are there as also a reference for this. Now, as I said, we want to consider it with respect to the Minkowski space. So we take the target to be Minkowski space. So you have your normal space like normal nu and time like normal n on your physical space, on the surface on the physical space here. And then you do isometric embedding, and you will have your normal mu's, 0 and n0 in the Minkowski space. Okay. Note that I'm not imposing any condition on the topology of sigma. I'm assuming there exists such isometric embedding. Even though I do not have a theorem which actually proves there's isometric embedding, I need to note here that there is no obstruction result which says that you cannot isometrically embed a surface with arbitrary topology in the Minkowski space. Okay. And there are also some results related to isometric immersion of a torus in like R4 by Yao and Gromov, classical results. Okay, so what is the quasi-local energy? So let's say you have this isometric embedding, and you have this T0, the observer in the Minkowski. You have the N0, the future-directed unit time-like vector field in Minkowski. You can write the quasi-local energy as a difference of Hamiltonian. So each one of these Hamiltonian depends on the sigma and depends on the gauge you pick, the observer and the unit time-like vector field n. So now there's a question, how should we choose this isometric embedding and how we choose this gauge, okay? And people use different isometric embedding, different gauge, end up with a different definition, okay? Let's go to classical result by Braun and York. They knew that there is isometric embedding in the Euclidean space if you assume that you have a sphere with a positive Gauss curvature. So they pick that, and they know this isometric embedding is nice enough, is unique up to the rigid motion of the Euclidean space by the classical results of Nirenberg and Progrolov. So they pick the observer T0 and 0 to just be dt, and t to be n in the normal directions. As a result, the lapse is 1 and the shift is 0. They get the following definition for quasi-local energy, which is the difference of the mean curvature in the Minkowski space and in the physical space of your surface of your surface. Now, Xi and Tam wanted to prove the positivity for this quasi-local mass, so they assume the surface sigma is mean convex, and then they could, assuming the dominant energy condition, which translates in time symmetric to non-negativity of scalar curvature, they could get the non-negativity of the Braun-York mass. Furthermore, they show that the rigidity happens if and only if you are a finite domain in the Euclidean space. Note that the proof is global proof, is based on results of Shane and Yao and Witten. So you construct the extension, the Bartnik extension or Shitan-Bartnik extension, and then you glue it to the original, manifold omega, and then you get the complete Riemannian manifold asymptotically flat, which you can get from the classical result of Shane and Yao. They have non-negative scalar curvature as long non-negative ADM mass as long as it has non-negative scalar curvature. So the extension they constructed has 0 scalar curvature. Furthermore, they show that the quantity is monotonic. On the surface is Braun-York, and at infinity is like ADM mass. Anyway, so there is another problem which we want to address here. And the problem is fine. It's by Shane. In 2018, Shane gave a talk exactly in this room. He raised a problem, and that was find a quasi-local proof of non-negativity of Broglie mass and related quasi-local masses. And so in this talk, I'm going to address the first problem, which is the Penrose problem, and the second problem, which is the Schoen problem. So here is the definition of our quasi-local mass with respect to Minkowski spacetime. What I will do, I will pick a future-directed constant null vector in the direction 1 and minus AI. So here AI is a vector on a sphere. So it has norm 1. And now I define a function. The function is the product of the position vector of the isometric embedding of the surface and in the direction of my L, the future-directed null vector. Okay? You can look at this completely different, in a completely different way. You can look at this like this function, which is sitting on the surface I of sigma, and also it's the same function by the isometric embedding sitting on the surface of sigma. It's actually the intersection of null hyperplane minus T AIXI to your isometric embedding surface. So you get a bunch of, for each A, you get these kind of different value for this function. Now I want to define my observer. So my observer is this null direction, okay? Which in the Hamiltonian, Hamilton-Jacobi analysis, you can pick a null or you can pick a causal direction, null or time-like. But I define my observer at this point to be time-like. So I define a sequence of observer. For each epsilon, I define the following observer. T0 will have the square root of, the norm of gradient of u, square plus epsilon square, in the direction of n0, which is unit future-directed time-like vector in the isometric embedding. And also my shift is just the boundary gradient of u. Okay? So this is the restriction of my observer, which is in that null direction, restricted to the surface of this I of sigma, okay? Note that if you compute the norm is minus epsilon squared. So if you take the epsilon goes to 0, this guy is actually a null vector, okay? But at this point, we're fixing epsilon to be positive, and we have a time-like observer. Now, I put my first assumption here, a second assumption. The first assumption was the isometric embedding. The second assumption is I'm assuming when you do this isometric embedding, the mean curvature of your isometric embedding is actually a space-like. This is nice because then I can go to my Hamiltonian and actually construct a unique frame. There's a unique frame, which I call that, optimal frame better, with the following condition. The contraction of this mean curvature vector in this time-like direction of the observer, which is time-like direction of the frame, which is E4 hat, can be expressed in terms of a Laplacian, boundary Laplacian of u, and gradient Laplacian of u, and also the mean curvature vector in the direction of E3 hat is positive, or outward pointing. You can say that. Okay. Note that this is called the optimal frame. What is the optimal frame? It actually gives you a maximum Hamiltonian to all possible frames which are outward pointing. So if you go to all of these outward pointing frame for the normal bundle, the optimal frame is the maximum, give you the maximum Hamiltonian. Now I want to repeat the same kind of game in the physical space. I can express it in terms of this equation. I call it a star. We will come back to this. Sure.
Yeah. So this maximum is like with respect to boost angle. We kind of relate these different frames, rotate these frames.
Yes, you can just go to any frame you want as long as they're outward pointing. As long as you're outward pointing and compute the Hamiltonian, and the optimal frame is the maximum of that. Give you a maximum Hamiltonian. So you can just, close it and just go to a different one by the Lorentz transformation.
Yeah.
Okay, So I pick my gauge. I already picked the T0. Now I pick my nu zero and n0 to be this optimal frame. And when I do that, I can re-express the Hamiltonian in terms of the mean curvature vector in the direction of this normal space-like direction, which is E3, gradient of u, the normal gradient of u, and something in terms of this frame, which is the connection one form of the normal bundle. Let's call that alpha, and in the direction of this shift. Okay. Now I pick my observer now. This time I'm in the physical space with the same lapse and shift. And there's a reason for that, because I want my observer will not recognize if he or she is in the physical space or if it is in the Minkowski space. So they have the same lapse and shift. And now this observer starts to compute the Hamiltonian. So I'm putting my second assumption, or if you assume the isometric embedding, my first one, and then the third assumption, and that is the mean curvature vector in the physical space is also a space-like. And outward pointing, then I can go to my Hamiltonian and again maximize it and get a frame, which is the optimal frame, with the property star, and it gives me the maximal Hamiltonian in the physical space. Okay?
Okay.
Yes.
Is this probably that you like this choice of this gauge, like that the observer actually can tell if he or she is the Minkowski space or in the physical space time? Is this kind of gonna give you some sort of gauge invariance at the end of the day? Yes.
Yeah, because exactly this would give me the main thing, which is the gauge invariant, and that is like you can express the energy only in terms of things which are gauge invariant. In particular, the Laplacian of u is just a function, norm of the mean curvature and mean curvature vector.
Right.
But if you go to the Bourne-York, the Bourne-York is gauge dependent because you pick it to be time symmetric and in terms of the mean curvature, which is you can change the normal and that will completely change the mean curvature. Now I picked this frame in the physical space to be the optimal frame, and now the same thing happened. Note that this curly edge is again quasi-local Hamiltonian density. The only difference is if you go back to the previous equation, you change the h naught to h, the mean curvature vector in physical space, and E3 hat to E3 bar in the physical space, and the connection one form in the physical space. So it's the same quantity in this frame. Good. Now I go to the work of Bootman, Bourne-York, and Hawking and Horowitz, and I take the limit epsilon goes to 0 because I want to compute the energy in the null direction. The reason I didn't do that at the beginning was if you go to the star, if you go to the equation of star, the gradient of u can vanishes on the surface. So there's a problem with there. But my hope at the beginning was when I integrate, I can just escape from this kind of problem. So, and that thing will happen, I will show you. So you take the limit, epsilon goes to 0. And now this will be our quasi-local energy. What is the quasi-local mass? You follow what you do in special relativity. You go through all of possible admissible observer, which I'm going to highlight in the next slide. And you minimize it, the energy. And this will give you the mass. Note that the argument that already highlighted is following Wang and Yao. They pick a different L. We pick the L to be null direction. They pick the L to be time-like direction. Their tau is our UA, and they could actualize the isometric embedding with the tau function. For us, this is still a kind of open problem. First of all, we don't know how to do the isometric embedding of, let's say, a torus in like Minkowski, and then find the connection between that with the UA. But in general, the UA and tau are they have the same definitions. Like in the sense, you only change the directions of L. For us, it's no light. For them, it's time light. Okay. Now, what is admissible observer? It's a topological condition. So to be able to maximize the Hamiltonian, I need the mean curvature in the isometric embedding to be a space-like. I already highlighted that. Let's put this in our admissibility condition. Now I'm assuming another one, which is called a regular level set of this function UA. All of them are maximal. And what does it mean? It means that you can find a filling. So let's say this picture is a torus. You isometrically embedded in the Minkowski space. You can find a filling like omega hat, such that when you intersect this with this null hyperplane, the intersection will give you a region here. Case of torus in this picture will give you 2 disks. But the boundary of that has 2 components, and you want the Euler number of the intersection to be maximal, and that means 2. Okay? So if, for example, if you cut it over here, you will get 1 disk, and you have 1 boundary component, and the Euler number of that disk is 1. So that's the maximal condition. As long as your surface is not very wobbly and crazy, this topological condition, if you have the isometric embedding, should actually hold. Because many of these isometric embedding will come up to some rigidity, like some isometry. So you can, if this one doesn't have it, you can slightly rotate it or change it such that get that condition. Okay. Now, there are several questions to ask about the energy and mass. The first one you can ask is, does the limit exist? Okay. Taking the limit, epsilon goes to 0. Does it exist? Is it finite? Does it have positivity and rigidity property that I listed? Does it have the value, the proper value that I'm looking for at flat or null infinity? And you can add more conditions too. Let me answer the first question, and that is the limit exists and is finite. Actually, you can show that. Applying the dominated convergence theorem, you can show that you can express the energy that I highlighted before in this form. Note that here we have only the norm of the mean curvature vector, so it's gauge independent. And the other things are just a function, and you're getting like boundary gradient or Laplacian of that functions. Here also there is like this sigma tilde, which represents a subset of sigma, which the boundary gradient is non-zero. Also, we have 2 functions, f0 and f. Both of them can be expressed in terms of the norm of the mean curvature vector. Laplacian of boundary Laplacian of u and gradient Laplacian of u. Okay, good. So we have a gauge independent one. Now, what is our theorem? The theorem is as follows. Take a surface sigma, be a closed space-like 2 surface in 4-dimensional space-time, satisfying dominant energy condition. Assume sigma has a space-like and outward pointing mean curvature vector, and it bounds, initially it's a compact region omega. We assume a topological condition, which is the second homology of that is 0. Now, if an isometric embedding together with UA is admissible, if you find that isometric embedding, if you find the UA with the topological assumption that we said, then the quasi-local energy is actually exists. It's finite and it's non-negative. So if you have a round sphere, clearly you have this isometric embedding. You can embed it in like Euclidean space, or you can embed it, let's say the Gauss curvature is negative, you can embed it in the hyperbola or hyperbolic space, which is like a hyperbola in Minkowski space. And then you can have this condition. So the energy is non-negative, that's good. We have the non-negativity. What about the rigidity? So if the energy vanishes for all A, then the initial data that you have, the quasi-local data that you have, which is the surface the metric, the mean curvature, and connection bond form actually arises from the Minkowski space. Now, if the surface is sitting in the Minkowski and you know the inclusion map is admissible with some function UA, then the mass is 0. So it has the other direction of the rigidity too. Note that the proof of this theorem is completely quasi-local. So it will address the Schoen problem. This is in contrast to all other quasi-local masses like Von York, Liu Yao, and Wang Yao. And also, sigma here, it's not a sphere. I'm not assuming it's a sphere. The argument of the proof works for any surface with any topology that you want. Now, let's look at asymptotic. For asymptotic, I'm picking asymptotically flat initial data set, so M, G, and K. Now, it's asymptotically flat because outside of a compact set is diffeomorphic to, ball, R3 minus a ball, and the metric and, second fundamental form K has the following decay. Here, I'm assuming tau to be bigger than half because I want to have a well-defined ADM energy and momentum. So assuming that the mu, the energy density and momentum density are integrable, we know the famous ADM energy and linear momentum are actually a well-defined quantity. Here, the ADM energy can be expressed in terms of the first derivative of the metric at coordinate sphere at infinity, and then linear momentum can be expressed in terms of the second fundamental form at face of second fundamental form at metric in coordinate sphere at infinity. Now, let's look at our limits. So I'm picking this asymptotically flat initial data set. I'm going to infinity picking the coordinate sphere. Since the coordinate sphere is very far, the Gauss curvature is positive. So I can use the Weyl embedding problem and at least embed it in the Euclidean space. Now, then I can start to compute my ADM energy, quasi-local energy for this coordinate sphere, and it will be in terms of E minus AP. So the minimum of you want to compute the mass, let's say this is your isometric embedding, you minimize it among all of this UA or A, you get E minus P. And this is exactly the ADM energy, the minimum of the ADM energy momentum vector in all node directions. So note that if you compare this with the result of Wang and Yao, you get the rest mass, which is the square root of P square minus P square, because that's the minimization along all of time-like, future directed vector. Now you can go to null infinity this time and pick for the space-time Bondi-Sachs coordinate. This is the coordinate expansion and you have functions in the metric like UV and WA, and they have the following decay. And the metric looks like this, the two-dimensional metric sigma. Then if you go to one of these null cone and pick a coordinate sphere, and that equivalent to W, coordinate W to be a constant, you can compute the Bondi-Sachs energy momentum. And Bondi-Sachs energy momentum can be expressed in terms of the M, which is showing up in the decay of V. That will give you the energy. And momentum can be expressed in terms of M and eigenfunctions of your, Laplacian on a sphere with the eigenvalue -2. So now what will happen to our quasi-local energy? You can go to one of these cone at the infinity coordinate. Again, because you're far away, the Gauss curvature is positive. You can do isometric embedding in the Euclidean space, and you can compute the energy, and the energy is exactly what you want, is E minus AP. So it has this property too. Now, there is a question about this UA. So in general, you are doing isometric embedding codimension 2 space. So sigma is codimension 2 in Minkowski. And you have 4 unknown. But when you look at the isometric equation, you have a symmetric metric which has 3 equations. So 1 equation left. Now, we follow what Wang Yao did. For them, there was something very nice and beautiful happen, and that was they had a function tau, and they could characterize the isometric embedding with this tau. So when they compute the Euler-Lagrange equation, they actually could address the isometric embedding. For us, we don't know the direct relation. We know how UA is related to isometric embedding. So we compute the Euler-Lagrange equation, and we get equations similar to them. Note that here delta minus and delta plus are Dirac delta distributions at the maximum and minimum. So you can have not more than points. You can have like a line. So you can look at this distribution like a line for singular level setup UA. Anyway, so we have our fourth equation. So if we can solve this, we can get our UA, the optimal UA, and we can put it inside the energy, and we get the optimal, the mass, which is the infimum. Now, so at this point, one can ask questions that what are the differences and similarities between the new one than the Wang Yao? Let's try to see. So the first one is Hamilton-Jacobi analysis. Both of them has this property. The second one is gauge independent. Both of them has this property. The positivity or positive mass theorem, Wang Yao only can prove the positivity for a sphere, assuming the admissibility condition, which is different from ours. We can prove the positivity for any topology, assuming the admissibility condition. The quasi-local proof, we have quasi-local proof, they don't. The isometric embedding, they actually show that they can prove this optimal isometric embedding equation. So, sorry, this is about the characterizing the isometric embedding. We cannot, we don't know how to do that at this level. Limit at asymptotically flat infinity, their answer is yes, for us is yes. Limit at asymptotically flat null infinity, the answer is yes, ours is yes. Limit at a small sphere, the Chen, Wang, and Yao, they proved this in 2015, it's a beautiful paper. We need to investigate that. The Penrose inequality, I did two work with Khoury and Yao and Lesord and Yao related to space-time Penrose inequality for quasi-local masses. So we prove with the Khoury and Yao a kind of Penrose inequality when there's a scalar alpha. There's a constant alpha. And with Lesord and Yao, we prove exactly the Penrose inequality as long as you have extra admissibility conditions. So it's a very restricted class of initial data set. But we still need to investigate. Multiplicity, as long as I know, I checked the literature, I could not find any result related to multiplicity of Wang Yao. For us is unexplored. Hoop conjecture. In the paper that I did with Lesord and Yao, we actually addressed the hoop conjecture. So we construct energy, and one side it was that energy, another side was Wang Yao energy, and you can get the hoop conjecture for admissible initial data set. What about horizon? Recall that when I define our Hamiltonian, I maximize the Hamiltonian. Our quasi-local energy, I maximize the Hamiltonian. To be able to maximize, I assume the mean curvature is a space-like. Furthermore, I assume the mean curvature is outward pointing. So I assume the mean curvature vector is outward pointing. That means the mean curvature is positive. Okay? So for horizon, the mean curvature vector is 0 if there are mods. If you are in the time symmetric, it's minimal surface. So neither of us has a result. There is a numerical work recently by Yao and his collaborators study a kind of merging of two black holes, and they try to go to horizon with constant CMC surfaces. So there's that result, but still open problem for both of these. Stability of PMT, there is no one explore the stability of rigidity of positive mass theorem for either of these, quasi-local masses. Solution of isometric embedding, there's another paper by Chen, Wang, Yao in 2014. they look at the analytic solution. So they assume everything, they assume analyticity, and then they look at the formal solutions and they show that actually they can solve it. And for us, it's still unexplored. And the other thing is minimizations. So the question is, when you have that solution, then where is the minimum? Like in the time symmetric, what is the minimum of the quasi-local energy? So there is a result by Miao that actually addressed the case of time symmetric, and there's another result by Chen, Wang, and Yao that address in the, I think, axially symmetric case that you can find the minimum. You still don't know. And the other thing to explore is other quasi-local masses. So, other quasi-local quantity like the center of mass, angular momentum. So we still need to explore. So these tables actually give a kind of comparison between these two quasi-local mass and energies. Okay, let me give you a sketch of proof of non-negativity. So the proof is very simple. I maximize the Hamiltonian. I maximize this quasi-local energy in the optimal frame. I want to go to a frame, which I call that a level set frame. And in the level set frame, I can prove this quantity is non-negative. In the case of Wang Yao, they did exactly similar thing. They had the optimal frame. They went to Zhang graph frame. And using Zhang graph frame, they show this guy is non-negative. And for that, they need also to characterize isometric embedding with this tau function and project it to the Euclidean space. So the Zhang frame works when you have that structure. Okay. Now, the next step, the first step is this, construct the frame. Second one is show that frame has non-negative energy. And then you're done. So this is our quasi-local energy. First, I picked the second part, the physical Hamiltonian. And I construct the frame. And I show that in this frame, this Hamiltonian is bigger than the Hamiltonian in the level set frame. So for that, we go to the very beautiful paper by Hirsch, Cazares, and Khoury. They study the positive mass theorem, the space-time positive mass theorem, using the space-time harmonic functions. So they show that if you have initial data set, you can solve the space-time harmonic equations. And U here is called the space-time, harmonic functions. Now, using this space-time harmonic functions equation, using the Buckner identity, using the trace of the Gauss curvature, using integration by parts, they get an identity. And those identity, the boundary term was the ADM energy. And the lower order term was exactly this guy over here, this one, which is non-negative because you assume down infinity condition U bigger than J. For us, in another paper, which we wanted to prove the positive energy theorem in asymptotically hyperbolic setting, locally, asymptotically, which are like a toroidal, we rewrite the boundary term in different form. And here is the boundary term, which can be expressed in terms of mean curvature, norm of the gradient of U, and boundary gradient of U, K. And also you have another integral over the places, open subset that actually gradient of U is non-zero. Now we want to actually relate the Hamiltonian, the physical space, to this boundary term. Okay, let's see how we relate it. We define our frame using the level set. We already know there is a function like U, so I can define it for each epsilon. I can define this frame. The epsilon, the E3 hat is my space-like direction. The E prime 3 is my space-like, and E prime 4 is my time-like, or the normal bundle. Now I put this frame inside the quasi-local Hamiltonian density. I get an expression which is very similar to the boundary term. The only difference is there is epsilon here and there. Now I take the limit. I show this guy is actually bounded by a L1 function, so I can use the dominated convergence theorem and take the limit. And my limit of the Hamiltonian, quasi-local Hamiltonian density is exactly the boundary term in the identity. And I know the boundary term of our identity is bigger than something positive plus the Euler number. Okay? What is this Euler number? Is the Euler number of each level set of this space-time harmonic function, which is cutting my omega region. Okay? Now we go back to the second assumption. The mean curvature vector I assume to be a space-like and outward pointing. Because it has this condition, I can minimize the Hamiltonian. And I get that in the level set frame, the integral of quasi-local Hamiltonian density is bigger than the integral of quasi-local Hamiltonian frame in the optimal one. Note that I said maximal in the previous thing. The difference because physical Hamiltonian is minus this expression. So it will flip. And in particular, it will flip over here. You can see that using this equation and previous identity, you can look at the Hamiltonian in the physical and express it in the level set frame. And then that's bigger than something positive plus the Euler number. Now I go to the second term in my energy. Now in the second term, the space-time harmonic function, the Minkowski space is exactly the U hat, is exactly those null hyperplane. So they satisfy the same kind of identity, but for them, mu and j is 0, and this equation which is showing up in the lower bound is also 0. So the Hamiltonian in the new frame, which I call that hat prime, which is a level set frame in the physical in the Minkowski space, is exactly the Euler number. Okay, so it doesn't have that positive, quantity. Now I'm using the fact because this no planar solutions of the box operator, then I can use that and show that when you take the limit epsilon goes to 0, the Hamiltonian, the quasi-local Hamiltonian density in the level set frame and in the optimal frame is the same. So a magic thing happened over here that in the Minkowski space they have the same Hamiltonian. The level set frame is the optimal frame. You can say it like that. Now I put it in my energy. So first is the optimal one is bigger than the level set one. It's bigger than the positive quantity which I'm getting from the lower bound of this one. It's getting the difference of the Euler number. And now you see why I had that visibility condition about the Euler number. So the first part is the maximum principle. You look at the PDE, elliptic one. By maximum principle, you know that the U hat and the space-time U, because they have the same boundary condition, they have the same maximum and minimum. So the limits of this integral are the same. The next one, you look at the topological assumption. The topological assumption will tell you the second homology is 0. So you have the level sets of your space-time harmonic functions. They can either go and hit the boundary or they can enclose a finite region. If they enclose the finite region, you can use the half maximum principle and get contradiction. So all the level sets will go and hit the boundary. Okay? And because they hit the boundary, at the boundary they are UA, so they have like n component. And clearly the Euler number is less than the maximal one, which is n. And that's the maximal Euler number condition we put there. So you get this is non-negative. So using the admissibility condition plus the dominant energy condition, which give you this is positive, it will give you non-negativity of energy. Okay. So that's the end of the proof for non-negativity, sketch of proof. But let me talk about the work that we are currently doing. So we are working to define center of mass and angular momentum. We are thinking how to solve this optimal isometric embedding, in the special cases. And the other thing is there is a result of, Miao, and also there's a result of Chen Wang Yao related to estimations of the quasi-local energy in time symmetry and axial symmetry. That's something else we are working on. The sphere limit, the smallest sphere limit, this is another one.
Are you working on the small sphere limit?
Let's talk about that. And the other things are like monotonicity and Penrose inequality. So note that our energy does related to a divergence formula. So there is a chance of, I don't know, some additivity or monotonicity. I hope you still did not explore it. For the Penrose inequality, the problem will get harder because the level set are like mostly like you can say it's in the asymptotic flat setting. If you go far away, it looks like a plane, so it will cut the horizon. So that's something it's not explored yet. Oh, that's all. These are the kinds of future works. Thank you.
All right, so we have this is the question time. So if anybody has any questions from the audience, please unmute yourself and ask Augel.
Sorry, I have a question. Can you explain a bit about the relation to spin geometry?
One second. Okay, increase the volume of the laptop.
Connected to my, I cannot hear. Just
Okay. Can you ask now? Hello.
Can I ask a question?
Yeah.
yes, go ahead. Yes.
Can I ask a question?
Sure.
Yes, there is a paper by Yao recently that he gave a spin geometry proof of this quasi-local mass for the quasi-local mass in 2009. Can you explain a bit about this proof?
Yes. I need to check that. Yeah, there is a proof. I need to go through that and check that.
Okay, thank you.
But this, I need to highlight that this proof is not like a Spinor proof. So, yeah.
Yes, because there he mentioned that he used only the topology of the surfaces for the proof, and in other proof of the positivity of quasi-local mass, they use somehow these quasi-local definitions.
So to come up with like none of these the other like quasi-local masses, they can address the other topology. This one actually works for the other topology. So when you go to the argument of the proof and the rigidity, you can do all the steps without even getting any kind of abstraction about the topology of surface, as long as you have the isometric embedding, which is itself, it's a really deep and hard geometric analysis problem. That to be explored. For the other result is a Spinor proof. I still need to check that to see. Yeah.
Thank you.
You're welcome. Any other question?
Do you have any more questions from the audience? Okay, if not, then let's thank Akhil again for the wonderful talk, and we'll see everybody next week.